Okay, so today I'm going to try to very quickly give you a flavor of Agile text mining. So despite quite a lot of very good efforts, there's still a huge amount of information in unstructured text. That's sometimes a fully unstructured text document, but often it's unstructured fields in Excel spreadsheets or in databases. There's the external scientific and patent literature, but also internal reports. Now, search technologies are designed to give you the best set of documents for a particular search term, but you then have to read through all those individual documents. So what text mining is trying to do is to save you time by more efficiently answering various questions you have. Things like which companies may be working on a particular target, what kind of chemicals are associated with a particular disease. The technology is used widely in the top 50 pharma, so the I2E solutions used, for example, in 9 of the top 10 pharmaceutical companies. So how does it actually save time? Well, if we take an example here where we're looking for genes associated with a particular disease, if we were actually doing a search, we would have to look for all the documents containing the disease and then look through each of those documents to find the genes of interest. If instead we can immediately look for all the different gene terms, so search for tens of thousands of genes, all their individual synonyms, we can then get a list out of all those different genes, and we can get the highlighted evidence for how those genes are related to the disease. And we may only need to read a couple of sentences to actually find the association between the gene and the disease. So we can check individual sentences such as these, see whether those sentences give us enough evidence or not, to then move on to the next gene. So that's much more efficient than reading the 470 documents for the first of the genes in the list, for example. So let's have a slightly different example. That was just giving us a simple list of genes. If we're interested, for example, in profiling, it could be a person, it could be a gene, it could be a chemical. We can actually summarize different properties of, in this case, the compounds, and pick those out of different documents. So here we've got things like cyclosporin treating psoriasis, and all of these are open out to give lots of other diseases that it's associated with. We're just seeing here the collapsed form where we're seeing the most common disease at first. But we can also pick up the particular dosages. We can pick up which genes or proteins it's inhibiting. We can look at things that it might actually cause, so rather than treat. We can look at what different genes and proteins it's affecting, and we can also pick up numerical information like IC50 concentrations. So that gives us a way of getting a sort of tailored profile of the chemical which is relevant to us. And it's not something you would get with a search getting you to the documents which are most about cyclosporin, because many of these documents may be instead about lymphoma, for example, where cyclosporin is only mentioned incidentally. So that gives an example where you're putting together different pieces of information from different documents to summarize. It's all known information. It's just maybe difficult to find within the literature. The other kind of thing you can do is actually start to piece together different pieces of information from different documents. So potentially you can find new associations that way, new mechanisms of action. And this is similar to the approach with the semantic web, where you're using standardized identifiers so you can link from one entity to another. So in this particular example, we're taking the particular compounds, cyclosporin, and then we're seeing which genes might be in a mechanism going from cyclosporin to the disease psoriasis. So for example, in the middle, we've got cyclosporin inhibiting IL-8, and then we've also got IL-8 affecting psoriasis. But those are from two different documents. So that mechanism may be a new mechanism. Probably not in this case, but this kind of thing is used by our customers, for example, with adverse events. They're not sure of the mechanism of action which is causing the adverse event. So you're looking for these indirect associations where you're tying together different pieces of information from different documents, something which you really can't do very easily by hand. So those are examples in the biological space and the chemical space, but also if you're interested, for example, with the substructure, so we integrate with ChemAxon substructure and similarity search, and that allows people to say, for example, if we're interested for a particular substructure, which proteins are inhibited by that substructure, we can actually do a query, we can draw a substructure, and then find all the different compounds available in the database which actually match that, and then we can actually look then in the literature to see if we've got some inhibition against the different genes or proteins. So that's an example of a current integration, and actually as part of the Chickle project, which I'll talk a bit about tomorrow, we're actually going further with named structure and clustering. So thank you. Please visit our table outside if you're interested in a demonstration.